So welcome everyone for our second part of the dynamical system session of the Colóquio, the 33, I believe, yes, the Colóquio Brasileiro de Matemática Colóquio. It's my pleasure to introduce our first speaker today. She's a postdoctoral fellow at the Institute for Research in Fundamental Science in Iran. I didn't say the name, Maryam Hosseini. Maryam obtained her PhD at the University of Gilan in Iran. Subsequently, she held a few postdoctoral positions, first at the University of Ottawa in Canada, and then in South America, in Chile, at the Universidad de Santiago, and at the Universidad de Chile. She has already visited in Brazil, in Rio, recently, 2019, I believe. She was our guest at the Seminário daí, well known here in Rio, and it was our pleasure to receive her here. And today she's going to talk about the topological rank of minimal dynamical systems of Cantor sets. Thank you, Maria, please.
Thank you. Thanks for your introduction, and thanks to the organizer for inviting me for this conference. It's my pleasure. As you said, my talk is about topological rank of dynamical system on Cantor sets, and I'm considering just minimal systems. So let me start by some notations and introductory stuff. The state space is denoted by X, which is a Cantor set, and we have the action of Z on X by a homeomorphism T. That is usually denoted in this slide by T. And we have minimal systems. As it is compact space, we have the orbit of every point dense. And I start by introducing by recalling and reminding you some of the basic examples of minimal Cantor systems. If someone has not worked on these topics for a while. The first one, and maybe the simplest example of a dynamical system, minimal dynamical system on Cantor set is an odometer. The odometers that in some texts, they are called adding machines. They are rotations on Cantor set. In fact, you have the map, we have the shifted space, one-sided shifted space, and the map is not shift. In fact, the map is an isometry that moves in every point by a fixed point in the space. That the point is this 1, 0, 0 forever. So the first time that xi, that this xi is not equal to 1, T will turn that to 1, and then it changes the previous components to 0, and then it doesn't touch the rest. For instance, a point 0, 0, 0 forever will be mapped to 1. The first time that is not 1 is the first component, so it will be turned to 1, and then the rest is untouched, and you will see the change of the previous components in this second iteration. That the first time that is not 1, that the component is not equal to 1 is this second place. It will turn to 1. The previous one changed to 0, and then it doesn't change the rest. So this is sort of, if we look at the clopences and components of the space, we have really a rotational behavior. So these are called rotations on the Cantor set. It could be defined algebraically by considering inverse limits of an inverse limit of finite loops on finite groups. If you consider, for instance, if you have two odometer, we have these finite groups Z2, Z2 to the power of n that are like canonically mapped onto each other. And then if you want to talk about a general odometer, it means that instead of 2 to the power of n, we have at each step that T is iterating on is acting on the space. We have the space partitioned into Pn components, and components are closed and open sets because we are in Cantor sets. So this is an inverse limit of the finite groups. This is the general form of an odometer. And these maps are phi n's between ZPn plus 1 and ZPn's. It is a canonical homomorphism. So these are the only isometries on Cantor set. In fact, any isometry on the Cantor set is conjugate to an odometer. Another basic, in fact, well-known examples of minimal system on Cantor sets are Sturmian systems, or you may have heard their name under Donjuel's map. Donjuel's map that you have on the unit circle, they have their like symbolic versions are this is, sorry, I forgot to say that if you consider the Bernoulli measure for the odometer, then the odometer will be conjugate with respect to the Bernoulli measure, will be conjugate to these interval maps. Interval map on, I mean, this is the unit interval, and you have infinite sub-interval. So with respect to Bernoulli measure, the odometer is conjugate to this. This is another picture for with respect to measure. And the other example, that, as I said, is the Sturmian systems. The Sturmians are, as I said, a kind of Donjuel's map on the unit circle that you consider the irrational rotation, let's say by alpha, and then you fix a point on the circle, and you just write down to see where the trajectory of the point Z go. When it meets this interval I1, which is 1 minus alpha and 1, you write for a letter like, for instance, B. And if the orbit meets its complement, you write another letter, A. So this Z hat is an infinite sequence. All its components are A or B, okay? So we are in the shifted space by 2 letters. So if you consider the closure orbit of this point, Z hat in the shifted space, which is a Cantor set, with the shift map, this is called the Sturmian system. And it is, in fact, the conjugate to the Donjuel map that you have if you disconnect the unit circle along the orbit of Z. Okay? So this system is conjugate to the irrational rotation with respect to measure. And the measure that it has, the invariant measure for this system is the one that gives to these two intervals. Is the one that it gives to the two cylinder sets associated to these two intervals the same measure as the two intervals have, 1 minus alpha and alpha. And for the other like cylinders or open sets, the measures are exactly equal to their frequency of the frequency of their appearance in this sequence. Okay. So this is an Sturmian system. It is the map was shift So it is a subshift. For instance, if we have, there's another way to represent them in symbolic dynamic. If, for instance, when the rotation number is the golden ratio, and the point, the first given point is the 0, the symbolic sequence associated to this Z will have such model, okay? This sequence can be produced by, like symbolically, like directly, by having this morphism. This morphism that is defined on 2 letters of A and B. It maps A to this word and B to this word, A and AB. So if we iterate, if we start from A, for instance, and if we iterate this morphism frequently, then we will get Z hat. And if tau acts on Z hat, nothing changed. It gives you Z hat. So this is called the fixed point of this morphism. This morphism is called substitution. It substitutes any letter to a word, okay? Or a word, sorry, to a letter. So if we consider this Z hat, the closure orbit of this Z hat, under the shift map in the shift space on the 2 letter A and B, then this system is the same as what we had in previous slide, and this is called substitution system this time because it was produced by a substitution morphism. Okay. You know that rotations, irrational rotations are sometimes considered as 2 interval exchange maps, right? These are the simplest form of interval exchange maps. If we have a general interval exchange map, I mean a K interval exchange map, then they also, all of them can be produced by, similarly like this, by just one substitution morphism, or they can be produced by considering a sequence of substitution morphisms. So in the first case, they are called substitution system, but if they are produced by a sequence of substitution, they are called S-adic systems. These are like symbolic dynamics notations, okay? So in fact, K interval exchange maps are like generalization of substitution systems. So the examples that I mentioned are, I talked about odometers and Sturmians or substitutions. Odometers are isometry and substitutions are subshift, so they are expansive. In fact, on Cantor set, expansiveness is equivalent to being subshift, okay? And it was Donarovich and Moss that they proved that a finite rank Cantor minimal system is either an odometer or a subshift. I mean, these 2 cases are, I mean, we have a dichotomy for all Cantor minimal systems, which are of finite rank. So this is, so a natural question is that, I mean, what is the finite rank? What does rank mean, in fact? So to talk about rank, I should talk about Kakutani-Rocklin partition for a Cantor system. Suppose that we have, we have a given point, x0, in the Cantor set. If you consider a Klopen set around that, then we can talk about the induced system on the Klopen set C. So by defining the first return time map to C on the space X, C will be partitioned into finitely many Klopen subsets that for each of them we have some, number as the first return time map for all the points in CI. So this will make towers on top of each CI. In fact, if you consider C1 to be the base of, the first line here, the first segment of line here, then its image under T is a homeomorphism. So its image will be a clopin set. And then when you continue at the time of H1, all the points should get back to C. So they may get back to C1, C2, or any other ones. One of the bases, okay? So we have towers, each one of heights HIs. So because the system is minimal, you know that you see, in fact, that this partition, this partition or union of clopin sets is invariant under T, because we see the image of all the points here. Since it is invariant and the system is minimal, it should be the whole space. Therefore, it covers the whole space X. So this is a partition of X, and it is called a Kakutani-Rocklin partition for the space X and for the dynamical system X and T. If we continue this work by a smaller clopin set around X0, let's call it by C prime. C prime is a subset of C that contains X0. We will have a finer partition, a union of finer Kakutani-Rocklin partition that is based on C prime, okay? And by continuing this procedure infinitely often, we will have all these bases converging to X0, and we will have a sequence of nested KR partitions that, in fact, generate. We can manage to generate the topology on the space X, and it, in fact, generates the dynamic that we have on X by T. So what is the rank? The rank is defined like this. At each step, we have, for each partition PI, we have a number of towers. Okay, so the number of towers will be the rank of that partition. If we consider the minimum rank of all the partitions, that will be the rank of the dynamical system, the Cantor minimal system that we have. Okay. So this is the topological rank of the minimal Cantor system X and T. Now, as an example, the odometer that I mentioned, the two odometer, we have the cylinder 0 mapped to 1. So we have a top, and then 1 will be mapped to 0. So we will have a tower of height 2. So this is a first tower that is, in fact, covering the whole space, right? All the points are started by 0 or 1. And then if we continue, if we want a finer partition, we will consider, the point that I fixed is 0, 0, 0, 0. So a smaller clopin set around this point X is cylinder 0, 0. So we have this trajectory for this clopin set. At the time 4, all the points will get back to the base, which was this cylinder. So we have a tower of height 4 that refines the previous tower, the previous partition, in fact. So we have two Kakutani-Rocklin partition in this picture for the two odometer. And then if you consider smaller clopin sets around the point X, you will have a sequence. All the time you have just one tower. So two odometer is of rank 1, right? For the other example, the Sumian one, that was generated by the substitution morphism tau. If I consider this point X and this clopin set around that, the cylinder AB, you see X belongs to cylinder AB. It starts with AB. Then by the first return time map, C is partitioned into two clopin sets, in fact, two cylinders, that the first one, it has first return time map 2 for all the points, and the second one is first return time map equal to 3. Therefore, we have these partitions. This red one is 1 tower, and this the green one is the other tower. So this is a partition with 2 towers. And the good news is that we have, we can continue this procedure by just having these, just 2 towers at all the steps, okay? So the Sturmian system that I have is of topological rank 2. In fact, all the Sturmians with any rotation number are of rank 2. And all odometers are of rank 1. Because, for instance, for odometers, Sturmians always have just 2 letters. And we have similar argument as we had for the previous example. And for odometer, instead of 2, 4, we will have Pn, Pn plus 1, and so on. So each time we have just 1 tower. And for all interval exchange transformations that we have K sub-interval on the unit interval, they are, if you write the symbolic version, natural coding of their orbits, if you just write down for each point, the sequence that mentioned that which interval the point is meeting, we will have a symbolic system, and it's of rank K or at most K plus 1. So they are finite rank. And these are, I'm like just listing some basic properties that odometers are the only rank 1 minimal Cantor systems. Any rank 1 topological minimal dynamical system on Cantor set is conjugate to an odometer. And this shows a little difference, or maybe a huge difference with the notion of rank 1 systems in ergodic theory. In fact, an rank 1 ergodic system can be weakly mixing. Maybe you have heard about Chacon system or Kakutani system that are weakly, they were the first examples of weak mixing, non-strong mixing system. They are all of rank 1. When you consider the Rocklin partition, measurable partition for them that modelize the system up to some epsilon. At each step, you can always have just 1 tower. So this is the difference. And the other point is that there is no upper bound for the topological rank of a Cantor system, because anyone can start by different point and different Klopen set, and therefore we don't know how many towers he or she will have in his construction, okay? So, but there is a lower bound. The lower bound is coming from operator algebra, and in fact, this makes connection between dynamics on Cantor set and C-star algebra. That is called dimension group. Dimension group for any Cantor minimal system can be defined by this. This is its dynamical definition. The quotient group of all integer valued continuous functions on X, mod out by all the co-boundaries. In fact, this part is the connection with the dynamic. The co-boundaries are all the maps that are that can be realized at G minus GOT. This shows the values of F on the orbits. And then this quotient is an abelian group. It is, in fact, you can consider a positive cone for that, and it will be an ordered group which has a unit element. The unit element is the characteristic function of the whole space X. So this unital ordered group is an abelian group, and therefore it has a rank. You can define a rank for it. It is the dimension of the vector Q vector space or on G, like any other abelian group. This is a lower bound for the topological rank of the Cantor system. In fact, when you have odometer, one can make computation to show that K0 group is contained in Q, and therefore, as a Q vector space, it is of rank 1. So the topological rank of odometers is the same as the rank of their dimension group. The same for Surmians. Surmians are with rotation number theta. One can show that the K0 group is Z plus theta Z. And you know that this group in R as a Q vector space it is of rank 2. You can generate this group with 1 and theta. So it's of rank 2. So again, the topological rank is the same as the rank of the dimension group, but this is not the case always. In general, we have a rank of dimension group less than or equal to the rank of T. If the equality happens, this will be, very, very good for us. It is an optimum rank, but there are many systems that their topological rank are strictly bigger than the rank of their dimension group. To see the example, I need to talk about Brattelli diagrams. You will see the example in some next slide. Some of the well-known properties of finite topological rank system is that, first of all, they all have zero entropy. And the number of invariant ergodic measures are bounded. The continuous spectrum as an additive subgroup of R has bounded rank. These two properties are in fact related to the rank of, when we have a finite topological rank minimal system, it means that the rank of their dimension group is also bounded. And that forces these two properties. And also the number of asymptotic, the number of pairs of asymptotic orbits will be bounded. I should have mentioned the references for each of them, but these are, in fact, well-known, and these two are recent. So the question is that, apart from these properties, what can we say about the topological rank of a topological factor of a finite rank system? Is it finite or not? To see that, I should, that is in fact the problem that we have solved with my colleague, Nasser Golestani, and the tools that I need are the, Brattelli diagrams and Vershik system. A Brattelli diagram is, as I had written, it is an infinite graph. The set of vertices and edges are partitioned into finite sets. Each set of EIs of edges happens between EI is the set of edges happens between VI and VI plus 1. And the range and sources for each edge shows that which vertex is, the edge is coming from which vertex in previous level, and range shows that where is it ending up. So I will show it to you in next slide. Yeah, in this picture, you see this is an infinite graph. In the first level, we always have one vertex. This is intentional. You will see it, the reason later. And for instance, this is the first level containing two vertices. And here I consider it stationary, but it could be growing or, there is no restriction on the number of vertices and also edges. And EI is the set of edges between two consecutive levels. We can have an ordering on the diagram. The ordering is partial ordering, and it is defined for all the edges that with same range. Okay, and for each vertex at each level, we have a partial ordering, which is lexicographic, on the edges that are ranged at that vertex. So if you see here for each vertex, there is an edge with minimum ordinal number and one edge with maximum ordinal number. If you by a well-known lemma in logic impact, Koning's lemma, one can prove that there are infinite paths on the diagram, that all their edges are with minimum ordinal number, and there are infinite paths that all their edges have maximum ordinal number. If the number of minimal infinite paths and maximal infinite paths are unique, then the Bratelli diagram is called properly ordered, like this. For instance, these blue lines is an infinite path, and it is the min path on the diagram, and the red one is the max path. Okay. We can have a space, topological space beside that by considering the set of all infinite paths. The infinite paths start from the top to the bottom, to the infinite, to the, I mean, it will be continued forever. And we have cylinder sets. Cylinders are finite paths. They start from the top and ended up at some fixed level. Okay. These are, this is the topology that we have, I mean, the basis of the topology. And this makes the space, the topological space, I mean, in fact, we have a topological space which is totally disconnected and compact, but it may have isolated points. If the, I mean, if we want to have a Cantor space, we need some more properties. So let's first define a homeomorphism, like dynamic on this space, compact space, which was defined firstly by Vershik. The definition is a generalization of definition of odometer. That was why I like focused on the definition of odometer. When you have a sequence which is an infinite path, each of these components shows an ordinal number of some age. The first time that this age is not maximum, that will turn to that will be added just by one, and I mean that age will map to its successor, and then the previous one will be changed to the minimum, and it doesn't change the rest of the sequence. Okay, for instance, here, if you want to see the image of this infinite blue path, infinite path, this is one, so it is min and max are the same. In the second level, this is one. This is not the maximum. This is not a maximum ordinal number, so it will tend to 2, and then the previous one will be minimum, which is the same, and it doesn't change the rest. So the image will be blue, and then 2, and then blue. Continue the same. Okay. This is a Vershik map. If we have, I mean, this gives us a dynamical system. It is a homeomorphism. The max path will be mapped onto min path, and this gives a compact dynamical system on this totally disconnected space. And in fact, we can have if we start from a Cantor set, and if you have a sequence of KR Kakutani-Rocklin partitions, then we can produce a Bratelli diagram associated to that. I can show it on this picture. We have sequence of Kakutani-Rocklin partitions. You see, we have 2 towers in the first level, and in the towers of the second level, all the towers of the first level are sub-towers of these towers. So we have, for each tower, we put a vertex. The first one is X, is the whole space. And then the ages shows that, and their ordinal number shows that where the towers of previous level will appear in the towers of this level, okay? So there is a correspondence between the sequence of, Cantor minimal systems and Bernoulli-Verschick systems, okay? If you start from any of them, we can have the other one. In fact, we have a conjugate. If you start from a Colóquio tower and define its Bernoulli diagram, and then considering the Verschick map on that, you will have a conjugate system to the original system. This is what this slide says. And if the Bernoulli diagram is simple, means that all the vertices at every two consecutive levels are connected to each other, then we will not have any isolated point, and the space is Cantor set, in fact. So the conjugacy, in fact, is meaningful. These are examples of Bernoulli diagrams for odometers and Sturmians. This is odometer, and this is a Sturmian. And this is the example that I mentioned. A non-expansive and non-odometer system is an infinite topological rank. And this was, in fact, the first example which was constructed for this question, that if exists any or not. So the topological rank, as the Bernoulli diagrams are like just imitating the Coulomb-Rocklin towers, we can define the topological rank by just using Bernoulli diagrams as the infimum number of possible, minimum widths for all Bernoulli-Verschick systems that are conjugate to the Cantor minimal system that we have.
Maryam,
and
I'm sorry, just to let you know that we are running a bit out of time.
Oh, okay.
Sorry.
5 minutes, right?
Yes.
Okay. So okay, I just arrived to the point that of our solution. What we wanted to know is the topological rank of a finite rank, a factor of a finite rank Cantor minimal system. What we consider is the relation between the Bernoulli diagrams of a system and its factor. In this picture, the blue diagram is odometer, which is a factor of the red diagram, which is a toplets. And there is when we have a factoring between the two Cantor systems, in fact, it was George Eliot and Mini and Gorestani that they proved that there should be a connection between their diagrams by using these local morphisms such that at each two consecutive level, all the rectangles should be commutative with respect to the orderings. Having these three morphisms, in fact, here I showed that, the commutativity should be with respect to the ordering that we have on the two diagrams. And then having this, one can show the connection between the factoring map between two Cantor minimal systems and a map between their ordered Bernoulli diagrams. And this is just an example. What we proved is that when we have two Cantor minimal systems, and if you consider their Bernoulli-Verschick representations, B1 and B2, then the rank of the factor, topological factor, is at most 3 times the rank of the extension. And this, in fact, answered the question of Moss, Durand, and Petit. And these are the ingredients of the proof. That's, I think, my time it is exactly 10:40. We just proved, we had a generalization of well-known Feynman-Wilf theorem, which is very useful in symbolic dynamics. That was for periodic words, we could generalize that for any words, that how can we produce a word in the shifted space with minimum number of generators, or let's say subwords. And then we proved that how can we make, how much thinning might be possible on a Bratteli diagram representing a Cantor minimal system. These are two consecutive levels of a Bratteli diagram of a dynamical system. We proved that we can, like by microscoping, we can make it thinner. And then the result, the proof of result by using these lemmas was like easy. In fact, if we have x and t and y and s, that was its factor with a factoring between them. And we have a point, we can choose 2 points, x, we can choose a point x and its image under the factoring map. We can produce Bratteli diagrams based on x and its image. And then we prove that we use our tools to prove that these two diagrams, there are this relation between the rank of the two diagrams. And then we have the dichotomy of Moss and Donarovich for all the factors of subshifting back. That all factors of Cantor factors of finite rank systems are either subshifts or odometer. And there is another result in symbolic dynamic that I don't have time to talk about there, like ingredients. Thank you. Sorry if I exceeded the time.
It's okay. Let us thank Maryam, please.
Welcome.
So before any questions, I give you a minute to talk about the last. My question is, please talk about the last corollary that we didn't have time to talk. And I think you want.
I passed the previous slides about S-addicts. So
okay.
It was just about S-addict subshifts. That these are, in fact, the general form of interval exchange transformations. And it was a question of, again, Moss and Durand, that if you have, a subshift that is on finite alphabets is not necessarily of, its rank is not the same as the number of its alphabet. It can be of infinite rank or finite, but not the same as the number of its alphabet. So we proved that it cannot be infinite. It will be definitely finite rank. This is useful in symbolic dynamics. Yeah.
Okay, thank you. So
okay.
Is there questions or comments? Please feel free to open your microphone or put on the text.
So I have a question.
Please, Yuri.
What is the exact relation between the finite topological rank and the number of invariant measures?
Yeah, it is the number of invariant ergodic measures. The invariant measures are, that it's a showcase simple X. And then dimension group shows that what is the dimension of that showcase simple X.
It's exactly equal to the dimension group?
It is, it is one to the rank of that.
Okay. And the dimension group is less than or equal to the topological rank.
Not the rank of dimension group. The dimension group shows that, because invariant measures are in fact traces on the dimension group. These are like operator algebraic notions. We have a group and we have a morphism from homomorphism from the group into R. These are, in fact, the invariant measures. And then it is proved that these homomorphisms makes us showcase simple X. And then the pure traces that are, in fact, the extreme points of that simple X are related to the ergodic measures of the Cantor system. Mm-hmm. And when the dimension group is of bounded rank, that showcase simple X is of bounded rank 2, and then it shows that the number of extreme points are bounded.
Okay, thank you.
You're welcome.
I think we have time for one more short question, if anyone.
So these models that you have, they don't, they do have some metric, not just the topology, right? So they have some metric because it's like a subshift or odometer. So
yeah, it is. They are meterizable. Yeah.
yeah, the meterizable. And I wonder when you say that conjugacies are the existence of this conjugacy, the theorem is about the classifications of these, right? So I wonder if the conjugacy is like holder or better than holder. Can you say something about the regularity of the conjugacy?
Sorry, I didn't get your point. Sorry.
So
You
you're
said that-
classifying all these, for instance, every minimal Cantor factor of a finite topological rank subshift is an odometer or a sub. It's topologically conjugated.
Yeah. It is topologically conjugate. Yeah.
Yeah,
So
but
you say that for how the conjugacy, appears. I mean, it is just by using the fact that if it is of rank, if it's of rank 1, I mean, if the Bratelli diagram is of rank 1, it is proved that it is it is conjugate to odometer, and this conjugacy is just by using exactly the topology. It is. You are right. There is a metric for this system, but the proofs are just topological. I mean, if you want to see how the proof is going on, it is just by using topology. I mean,
I see.
So we use we consider like infinite paths and then finite paths. These are all like closed sets, and we just look at their images. But as long as I remember, we don't use the metric and the distance in the proof.
Thank
So
So it means that Daniel's question can be worked. I mean, his question is that is the conjugacy, can we prove that conjugacy is kind of a holder, something regular?
Oh, holder. Sorry, I didn't hear that.
English
Sorry, I didn't hear that. That the holder.
Yes. So you are topological.
We are on Cantor set. Holder, yeah, okay.
You have a metric space.
Yeah, it is metric space, yeah, but the proofs, yeah, as long as I remember, no, there is. I didn't see in the Moss and Donarovich proof that they said that it is subshift or odometer. I think they didn't talk about like metric properties of that.
okay, so thank you, Maryam. Let us thank her again, please.
Thank you.
Yeah.